Hi there. As a hobbyist, I've been building a lot of flying things just for fun. It's not a business or anything. I just like doing this as a hobby. So I build a lot of flight control computers for quadcopters. So today I want to talk to you about designing a helicopter, a conventional helicopter, using an Excel spreadsheet. Hi there. This is my home lab where I build a lot of electronics for my flying things, mostly quadcopters, and working on different electronics to do some different applications. But today I want to talk about the design of a helicopter, the basics of it, a simplified way of doing it using Excel spreadsheets. I couldn't find any books or much on the internet that would show you this process. Today I'm going to delve into it for you a little bit to try to teach you a little bit of this. I previously gave some lessons on designing an airplane and a lesson on propellers previously. So this is my third in the series, and this is going to be basic conventional helicopter design. So this would be a helicopter that has a main rotor and a tail rotor. Most of the helicopters that you see out there are, in the sky, as you look up in the sky, most of the helicopters you see are like that. So anyway, I'm going to move forward and get started with this lesson. Okay, so today we're going to talk about conventional single rotor helicopter design using a spreadsheet. So this paper provides an example of a simplified performance analysis for a conventional helicopter using Excel spreadsheets. It is an example on how to get started when designing a conventional helicopter which has collective, longitudinal cyclic, and lateral cyclic controls through a conventional swash plate. So this is a typical helicopter where its main rotor has a swash plate where these three control inputs can be provided: collective for vertical motion, longitudinal for forward and aft motion, and lateral cyclic, which would provide left and right motion. So as more details are discovered, they can be added to this analysis. So for example, as more things are found, different drags, different sources of drags, other sources of lift, other details, the skids, things that you could add into it, they could be added to this analysis so that more details can be analyzed. So this analysis examines the aerodynamic forces and torques based on basic helicopter design parameters. The parameters and equations are placed into a spreadsheet for analysis. So in this case, we did two spreadsheets for analysis. If the forces and torques can be balanced out or deemed sufficient, the design can be considered feasible and further optimized by parametric variations. So the trick with this is to try to see if you can balance out the forces being, say, the weight from gravity, the forces from drag. If you could balance those out and you have some overhead where you could generate forces to overcome the weight of the aircraft and the weight, the thrusts, the forces that are needed to overcome drag, then if you could show that you could overcome those forces, then you could say, well, the design is feasible. Just wanted to note, this is different from a simulation of the helicopter in that it does not examine dynamics of motion of the helicopter. So this isn't the same as writing a helicopter simulation in that that would probably come later. This is more basic. However, it would be the first step used when considering a configuration for a conventional helicopter design. So you would want to do this first, and then from this, then maybe a simulation of the helicopter could be developed where more details of the dynamics of the motion of the helicopter can be investigated. So the spreadsheets used in this analysis, we used two spreadsheets. So in this analysis, two Excel spreadsheet files were used. This one is called cyclic studies. So this examines collective and cyclic inputs for one rotation of the main rotor, and also examines the tail rotor. So this is looking at the details of the main rotor with respect to collective and longitudinal and lateral cyclic inputs. It also looks at the tail rotor to see if that would also be sufficient. And the next spreadsheet, this was set up for a four-bladed helicopter. It provides a method for parametric analysis for the helicopter design. So this is when you start adding drag and look at the airspeed and try to see is this feasible? Can the forces generated by the rotors overcome the drag forces and the weight of the aircraft? Okay, so this paper will examine the equations for a simplified single rotor helicopter with a tail rotor design. So that's what I consider the conventional helicopter, the ones that you see a lot out there, fly by all the time, and they have a tail rotor and one single main rotor. Now we could also do analysis for tandem rotor helicopters and tilt rotor helicopters and all other configurations. It would be similar to this, but you would have to reconfigure the analysis to match that helicopter. So in this analysis, it is assumed that flapping and feathering angles have a one-to-one relationship at 100% RPM. However, flapping lags the feathering input by 90 degrees for cyclic pitch. So there's some amazing things about cyclic pitch, and I would hope to give a presentation on that, on why flapping lags feathering. As the rotors spin around, you put a pitch input in. That's what feathering is the pitch input. But there's a lag where it's when the azimuth of the rotor is 90 degrees from that input, that's when the flapping goes in. And that's what really controls the helicopter, is the flapping rather than the feathering. So I hope to give a presentation on that someday, and so you can learn the details on how that works. But right now we'll just assume that's the way it works for this analysis. So for our main rotor, there's three inputs. So we call theta COLL the collective pitch input, and that's where all the blades have the same angle. And then we have theta long is our longitudinal cyclic input, and that would allow us to control forward and aft motion on the helicopter through the main rotor system. And then we have lateral cyclic pitch, and that would allow us to provide the left and right motion. What it provides is the forces. It provides left and right forces, lateral forces to overcome the drag of the aircraft. And the longitudinal would provide our forward motion to overcome the drag of the fuselage mostly. And collective pitch is our vertical input that allows us to overcome mostly the weight from gravity and allows us to make the helicopter go up and down. So I'm designating X as the blade number. So we have to have at least two blades. You have to have a way of balancing the rotor system. So a one-bladed helicopter may be possible if you had some kind of counterweight, but probably wouldn't be very efficient. But it is possible to have a one-bladed helicopter. But anyway, in our example, we're going to do a four-bladed helicopter. So X is the blade number. So this is the equation for total blade pitch down here. This would be like the total pitch going into the blade. In the case examined, there are four blades in the main rotor. So X is set to 1, 2, 3, 4 to designate each of the four blades. However, a similar analysis can be performed for main rotor if any number of blades. The blade pointing in the same direction as the nose of the aircraft points is considered the 0-degree blade. So anyway, there's an equation here, which is the total pitch of the blade. So it's the sum of the collective plus the longitudinal input, and it's a function of the cosine of the azimuth of the rotor disc plus the lateral cyclic pitch, which is a function of the sine of the azimuth of the rotor disc. So I just also pointed out that the blade that points in the direction of the nose of the aircraft, as we'll see in the following figure, is considered 0 degrees. We just had to pick, it's kind of arbitrary, but we picked that as 0 degrees to make this equation work properly with a four-bladed rotor system. So this is a figure that shows the top view of a four-bladed main rotor conventional helicopter. And I'm going to zoom out here a little bit so you can see the whole figure here. Okay, so this is our main rotor disc, and in this particular example, we're having it turn counterclockwise. I believe in the United States, the helicopters, the convention is that the rotor systems turn counterclockwise, and I believe in Europe they use a clockwise. Their helicopters turn clockwise when looking down. But anyway, it's kind of arbitrary, so we'll consider a helicopter that turns counterclockwise. So this is a figure. This shows the main rotor, and this shows the tail rotor. And we have a x-axis, a y-axis, and our z-axis. This is pointing down, say, towards the center of the Earth. This is really in the vehicle axis, so it's really pointing down relative to the vehicle axis. So anyway, in our case, we have four blades here. So we designate this one as our 0-degree blade, and this would be our 90-degree blade, and this would be our 180-degree blade, and this would be our 270-degree blade when the 0-degree blade is pointing in the direction of the nose. So we have some parameters here. We have X, L, and X is the longitudinal force, and L is the rolling torque. So this is the positive directions for these forces and torques. U would be considered our forward velocity, and P is considered our roll rate, and phi would be our roll attitude. So this is a standard convention for the polarities used in many aircraft conventions. So we also have our y-axis, that's lateral. This is longitudinal. So our y force is the force in the lateral direction. Our m torque is our pitch force. So go in this direction. Normally, the direction that tends to pitch the nose up of the aircraft is positive, and v is our lateral velocity, q is our pitch rate, and theta is our pitch attitude. So this is a standard convention that's used. This axis system, I believe there's like 12 different possible configurations you could look at these axes at for three-dimensional space. So this is the standard one that's used for aircraft. And z points down, so our z force is pointing down. That's our vertical force, and n is our yaw moment going around the z-axis, and w is our yaw rate, not yaw rate. That's our w is our vertical velocity, and r is our yaw rate, and this psi over here, Greek letter psi, represents the azimuth. So this rotor is spinning around, and it's spinning. It's actually spinning counterclockwise this way. So the rotor is spinning counterclockwise. And we also have v. This would be our forward velocity. And if the aircraft was hovering, this would be 0. But if we're moving forward, this has a value to it. So this is called our advancing side. So the velocity would be maximum with forward motion. This tip would have a high velocity, and this tip, the retreating side, would have a lower velocity. Other things I pointed out: the center of pressure of the rotor is 3/4 of the radius. So to do our simplified analysis, we always look at the forces acting on this 3/4. From the root is 3/4 of the radius. So if each blade here is 20 feet, this point would be 15 feet out. So this is I did a presentation previously on propellers and rotors, and we got into why it's 3/4. So this is where our forces act. Our lift, we could say, the lift is really distributed among the rotor where there's higher lift further as you go out. It has a parabolic distribution, but if you simplify it, you could look at it as a point being 3/4 of the root. So we come up with this thing called average dynamic pressure on the rotor, and all the forces work on that point. So that makes it a lot easier for us to analyze. So we have a chord of our blade. We picked 2 feet, and this is part of the design process. You take a guess at first, and then you refine it on the parametric analysis. So you take a guess of this. So I'm guessing, 2 feet is maybe a good chord, nice round number, and 20 feet is a good radius. So from there, depending on your requirements that you're trying to shoot for, you could tweak these back and forth in the parametric analysis to figure out, what gives you the best performance. So we're also talking about the tail rotor. So the tail rotor is used for anti-torque, and it generates a thrust. So we'll talk about anti-torque a little bit. So what's going to happen since the drive system's in the fuselage? When this rotor turns counterclockwise, it's going to want to make the fuselage turn clockwise. So it's going to want to make the fuselage turn to the right. So we have this tail rotor. You need it, which is a waste of power, but this is the most common helicopter out there. So to prevent, so what's going to happen? The fuselage is going to want to tend to turn clockwise. So we generate a thrust in this direction by the tail rotor to try to pull the fuselage clockwise, to put a clockwise torque on the fuselage to stabilize this. So without this tail rotor, with the rotor turning counterclockwise, the fuselage would tend to turn clockwise. So this propeller tail rotor here is set up to blow air in this direction to keep the fuselage from turning clockwise. So it generates thrust in this direction. I call the thrust LT, which is lift. It's basically lift from the tail rotor. That's why it's LT. And there's a crank arm here I call the DT, which I set arbitrarily to 40 feet. So it's the main rotor to tail rotor distance. So this is the crank arm that would provide this end torque, the end torque that would be applied to the system. So note that the end torque from this lift is negative because it will tend to turn the fuselage counterclockwise, and clockwise is positive and with this convention. So we want to talk a little bit more about the anti-torque feature of a conventional helicopter, at least the wording for it. So we'll talk about that a little bit. So looking at the top view, should the main rotor turn counterclockwise, the fuselage will tend to turn clockwise, since the power drive generation is located in the fuselage. So if we were going to visualize that, as this rotor system is turning counterclockwise, it's going to want to make the fuselage turn this way, clockwise. Therefore, the tail rotor is designed to counteract the fuselage's clockwise motion by applying a torque that will tend to torque the fuselage counterclockwise. So it's going to apply a force here which will tend to put a torque that will put a counterclockwise torque on the fuselage to keep this stable, keep it from turning. The torque applied must be equal to the torque generated by the total drag of the main rotor to keep the helicopter from turning right, which is clockwise. So basically it's the torque's generated off of the drag of the main rotor that tends to make the fuselage turn clockwise. So we put a counterclockwise torque on it to stabilize it, to keep the fuselage from spinning. So the torque applied will be negative and tend to turn the helicopter to the left, counterclockwise. The tail rotor is also used for directional control, so it's also a good way to control the direction of the nose of the aircraft. So when the tail rotor force is higher than that required force to keep the helicopter from turning right, counterclockwise, the helicopter will turn left. So if we make this force higher, this thrust has a bias on it to stabilize it. So if I want to turn the helicopter to the left, I increase this thrust, and the helicopter will turn more counterclockwise. If I want the helicopter to turn to the right, I'll reduce this, and this will turn the nose to the right. So you're actually reducing this thrust, and then because of the torque from the drag of the rotor, that'll make the helicopter turn to the right. So when the tail rotor force is lower than the required force to keep the helicopter from turning, the helicopter will turn right, clockwise. For a main rotor that turns clockwise, the reverse is true. So if your main rotor turns clockwise, in this figure we have one that turns counterclockwise, but there are helicopters that also turn clockwise. The reverse is true. Now this is just for a conventional helicopter. In helicopters that have two rotors that turn that are counter-rotating, this torque gets canceled out, so it doesn't apply. It's just for this conventional helicopter. Okay, the other exception is if the power generation drive was located in the rotating rotor system instead of the fuselage, the anti-torque tail rotor would not be required. So we're saying if the power generation that turns this counterclockwise was all within this rotor system, then there wouldn't be a need for a tail rotor. So there are some helicopters that had been designed that could do that, by putting jets on the end of the blade. And also another example is where you have counter-rotating blades. There's some helicopter designs, I guess, that have counter-rotating blades, but they're right on top of each other, and that would also cancel out the problem with that anti-torque. So now we're going to talk a little bit about longitudinal cyclic pitch. In fact, I'll put that up here. We'll say, put a little note up here. Title, longitudinal cyclic pitch. We'll make that bold. Yeah, let's make that bold. Okay. So anyway, so we have a side view of the helicopter shown in this figure without any longitudinal cyclic pitch. So I'm going to talk a little bit how that works. So we have our x-axis is here along the nose of the aircraft, and our y-axis comes out the right side of the aircraft, and our z-axis points down, and we also have our tail rotor. So due to the weight of the aircraft, the rotor system cones up a little bit, so there's a little bit of angle here, and this angle is really proportional to our our collective pitch. But right now we're just talking about longitudinal cyclic pitch. So anyway, the rotor system tends to cone up. So this is the lift, say for blade 1 and blade 3. I'm going to zoom in here a little bit. So this is an example where the longitudinal cyclic pitch is 0. And what happens, we generate this X force. So we call this X1 because this is blade 1. And we call this X3 because this is blade 3. So in this case, the X forces cancel. They're equal and opposite when the longitudinal cyclic pitch is 0. So this is how we try to control the aircraft longitudinally. It starts off with the longitudinal cyclic pitch. Now, as the aircraft pitches up and down, you could also generate X forces, but to get there, to try to change, you have to change the pitch attitude, and to get there, you have to have the capability in the rotor system to vary your X force. So I'll show how that's done a little bit. So we'll look at this figure here, and then we'll read the text. So this is a case where there is some longitudinal cyclic pitch. So what happens is this flapping on this blade is now higher. It's a higher angle here, and this one is a lower angle. So you can see these vectors change because of this is a lower angle. There's less lift on this blade, and higher lift on this blade. So this is our blade 1 and our blade 3. So here you can see now our X3 is higher than X1. So the resultant force would be basically X3 minus X1. So this is done through the swash plate, and we'll look at the details of that in our spreadsheets pretty soon. So we'll take a look at the details of that. So I'm just going through kind of the physics of it. So there's going to be resultant X force that's going to be able to move this forward, but we also have a drag force. So we want to make sure we can, in our analysis, we want to make sure that we could generate enough resultant X force to overcome the drag force. So if we can do that, then it's a good design. If we can't do it, then we're stuck and we can't move the helicopter forward. So I'm going to read the text up here. So it says, a side view of the helicopter is shown in the next figure with longitudinal cyclic pitch to force the helicopter to move forward. Note that the positive X force in blade 3, this would be blade 3, is greater than the negative X force in blade 1. So we call this a positive force because it's going in the positive X direction, and we call this a negative force because it's going in the negative X direction. So it says, note that the positive X force in blade 3 is greater than the negative X force in blade 1. Therefore, the helicopter can now move forward. A larger X force can be generated as pitch attitude of the aircraft changes. However, to get forward or aft motion started, the longitudinal cyclic pitch X force generation must be sufficient enough to get the forward motion started. The longitudinal flapping is generated from the longitudinal cyclic pitch of the rotor with a 90 degrees phase lag at 100 RPM. So the longitudinal cyclic is put in 90 degrees before, so it's actually put in when it's over here, and then as a blade gets to this position, it reduces this X force. So it has also been found that flapping and feathering has a 1-to-1 relationship. So that's also at 100% RPM in conventional helicopters. If I give it a 1 degree of longitudinal cyclic pitch, it gives me a 1 degree flapping input. So for every degree of feathering from the longitudinal cyclic pitch will result in 1 degree of flapping, but shifted by 90 degrees. It has been found that for a fixed longitudinal cyclic pitch angle, X force for each blade varies. However, the resultant total X force will sum to a fixed value as a function of longitudinal cyclic pitch. So what we're trying to say here, as this rotor system turns around, these X forces are going to vary all over. It's a sine function, but when you sum them all up, they equal to pretty much a constant. So it has also been found that the aerodynamic forces from dynamic pressure generated in forward flight sum to 0 for both the main and tail rotors. So that's another neat thing about the helicopters. Because this is spinning, as you go forward in velocity, your dynamic pressure is going to get higher. That it would be the dynamic pressure that would cause drag, say, in a conventional aircraft. But what happens, because this rotor system is spinning, it cancels out the dynamic pressure from moving forward. The impact to drag, it causes drag on the fuselage, but it doesn't cause any drag on this rotor system, on the main rotor or the tail rotor. So we'll look at that a little bit also in a little bit more detail in this lecture. Now, also, I guess we didn't talk about it as much, but the aircraft has a weight, so our collective pitch is generating a Z force in this direction to counteract the weight. So we'll talk about that also in our analysis. Now, likewise, like the longitudinal cyclic pitch, lateral cyclic pitch works in the same way, but it's a front view of the helicopter now. So this is a front view of the helicopter. So our tail rotor is now back here, and this is our Y. axis going out of the right side of the aircraft, and we have our x-axis, which is the nose, and our z-axis, which points down to the vehicle. So a front view of the helicopter is shown in the next figure without any lateral cyclic pitch. Note the lift to the helicopter's weight. The rotors will cone up slightly. So due to the weight, these rotors are going to cone up, which collective pitch is creating a z-force to cancel out the weight. Note that the y-force generated from the main rotors are equal and opposite and will cancel out. So this is with zero lateral. There's no lateral cyclic pitch. So the y-force cancels out with zero lateral cyclic. So you can see this y is positive, going in the positive y direction. So y2 from blade 2 is going this way, and y4 from blade 4 is going that way, but they're equal and opposite and canceling out. So as this rotor system moves, the blades are exchanging these forces. So you have to visualize that. Like what's shown in this figure it's true for an instant in time where the main rotor or blade 2 is out here at the 90-degree position and blade 4 is at the 270-degree position, but these blades are constantly moving around. So say blade 1 turns into this position, and so it would be the y1 force at that point would cancel out the y3 force. But these vary in a sinusoidal motion as this blade system turns. So lateral cyclic pitch is very similar to longitudinal cyclic pitch in how it works. So we're going to look at the figure now where we want to go to our right. So we put some lateral cyclic pitch in. So this is a case where the lateral cyclic pitch causes this blade 2 now to have a higher flapping on this side and a lower flapping on this side here. So what happens is the lift becomes higher on this blade and lower on this blade. So we generate the y2 force from blade 2 is greater than the y4 force from blade 4. So this causes the helicopter now to move towards its right. The picture is a little confusing. We see it going to the left, but because we're looking into the nose, it's moving the opposite direction from what we see, what we perceive. But anyway, this would be considered going right relative to the body axis of the aircraft. So for lateral cyclic pitch, with a lateral cyclic pitch, y2 is greater than y4, thereby a net lateral force is created, which would move this helicopter to the right. Now if we wanted to go to the left, we would put an opposite lateral cyclic pitch in, which would cause this blade to come up and this one to go down, and that would cause y4 to be greater than y2, which would move to the left. So I want to read some of the text here to make sure it makes sense to everybody. So a front view of the helicopter is shown in the next figure with lateral cyclic pitch to force the helicopter to move towards the right. Note the positive X force in blade 2 is greater than the negative force in blade 4 over here. Therefore, the helicopter can now move towards the right. A larger Y force can be generated as the roll attitude of the aircraft changes. So as we roll the aircraft from a rolling moment, that would also generate some thrust vectoring from the rotor system that would allow a bigger Y force, and that's the kind of thing we would want to study in our simulation. But for this analysis, we just want to get it started. So we need to generate Y force when there is no pitch attitude and the aircraft is level to get things started. So that's what that pointed out. However, to get the left or right motion started, the lateral cyclic pitch Y force generation must be sufficient enough to get the lateral motion started. The lateral flapping is generated from the lateral cyclic pitch of the rotor with a 90 degrees phase lag at 100% RPM. It has also been found that flapping and feathering have a 1-to-1 relationship. So for every degree of feathering from lateral cyclic pitch will result in 1 degree of flapping, but shifted by 90 degrees of azimuth. It has been found that for a fixed lateral cyclic pitch angle, the Y force of each blade varies. However, the resultant total Y force will sum to a fixed value as a function of lateral cyclic pitch. So what we're saying is that these Y forces vary all over on the blade itself, but if you sum all 4 blades, it becomes pretty much a constant relative to lateral cyclic pitch. It has been found that the aerodynamic forces from dynamic pressure generated in lateral flight sum to 0 for the main rotor. So just like longitudinal, system, if you get lateral velocity, either left or right, it doesn't impact the drag of the main rotor. At least and the basic theory says that. Maybe more detailed theory, due to all kinds of turbulence in the flow, and if you get negative dynamic pressure, things like that happen, and you could stall. At certain points the blade stalls out. But anyway, for the most basic theory, it says that as we move to the left or the right, the dynamic pressure due to the motion doesn't add any more drag to the rotor system, the overall rotor system. It does to each blade, but not to the whole rotor system, because it cancels out, because one blade goes one way, the other one goes the opposite way, so the drag forces pretty much cancel out due to dynamic pressure going left or right. So now it's time to start talking about some of the math behind this. So for a 4-bladed helicopter as presented in this example, the blade angular azimuth offsets are, so for the first blade, which is at 0 degrees, the offset 0, and the second blade is pi over 2, which is 90 degrees. The third blade is pi, which is 180 degrees, and the fourth blade is 3 pi over 2, which is 270 degrees. Now in our example, we're going to do the 4-bladed helicopter, but if you did have a 3-bladed helicopter, this is how you would do it. You would break everything by 120 degrees. So this was just an example if you had 3 blades. So anyway, the lift for each blade is going to be the coefficient of lift, which is 2 pi, because we consider everything as just being a flat plate, times the average dynamic pressure, times the surface area, times the pitch of the blade. So these x's represent, say, blade 1, 2, 3, or 4, and this is the pitch of the blade for blade 1, 2, 3, or 4. So these are all the same constants pretty much, and this is the only thing that varies. So that will get you to lift. So the pitch up moment, that's m, that tends to make the aircraft nose up, is going to be 3/4 times the lift times the cosine of the azimuth of that blade. So this is the moment that is generated by each blade. Maybe I'll go back to the figure and we'll take a look at maybe how that might work. So if we go back to the figure, say for blade 1, the lift works at this point here, and it's 3 R over 4, that's our crank arm. So for the set moment, you could see it's going to maximize here. Of course, when it goes in this position, the lift at that point has no impact on the M moment. It does impact the L moment, and then when it's over here, it does. The lift will tend to make the aircraft nose down. Over here, it makes the aircraft nose up, and when it's at this position, it has no impact on M, but every place in between it has some impact on M. So to capture that, it's 3R over 4 times the lift. So this is our crank arm, and this is the force, and this is the azimuth impact. So we sum all our 4 blades up, where N is equal to 4. That's the N represents the number of blades. So our total moment at any point in time is the sum of the four for a four-bladed situation. Now for our rolling moment, which is represented by L, it's very similar, except you use sine instead of the cosine. So it's the same equation again. There's four blades, and you add all four blades up, and we get our total rolling moment. Now our end moment, that's strictly from the tail rotor, is just the crank arm of the tail rotor times the thrust developed by the tail rotor. Notice it's negative because it used the fuselage in a counterclockwise direction in this example. So our Z force is going to be, since the direction of Z is pointing downwards, it's minus lift times the cosine of the flapping angle, or flapping and pitch of the blade are proportional, has a 1-to-1 relationship. And so likewise we sum all four of our Z forces together to get the total Z force, and we'll look at the figure again to look at that to try to understand it. And for our X force, it's the lift minus the lift again. It works out that way, times the sine of the pitch angle of the blade times the cosine of the azimuth. And likewise, our Y force is the lift times the sine of the pitch blade again times the sine of the angle. So likewise, you have to sum all four X forces for all four blades up and all Y forces for all four Y blades. And we'll take a look at the figure again to reinforce that. So if we go back to the figure, you could see, our Z forces, it's the cosine of this angle. So that this would be theta 3, and this is theta 1 in here. So you can see it's the cosine of the lift would give you this resultant, and the Y is the sine of that angle. So here's the nose view of the helicopter again, looking at the lateral Y force. So likewise, the Z force again is the cosine of this angle, say theta 4, and on this side it's theta 2. And the Y force, say an example for Y4, is the sine of this angle. See, it's that one. The small one is the sine of the angle, and this would be the cosine of the angle times the lift. So we're summing all these forces and moments up, and what we're going to try to do for the design is make sure they're sufficient to overcome the drag, to overcome the weight, and the moments are sufficient to generate a good, in case of M, a pitch moment control, and for L would be a rolling moment, and for N it would be our yaw moment. So one other thing I wanted to show you is that there's additional dynamic pressure from the motion of the aircraft. So I wanted to talk about that. Additional dynamic pressure from longitudinal or lateral flight. So the average dynamic pressure of the main rotor blade working on the center of pressure and hover is, we computed this previously in a previous lesson. So the Q average is equal to rho omega squared r squared over 6. However, there's additional dynamic pressure from airspeed and longitudinal or lateral flight. So if you're hovering, that's the case, but if you're moving longitudinally in forward flight or laterally in lateral flight, there's an additional dynamic pressure. I call it Q add, and that's 1/2 rho v squared. For a conventional airplane, that's not a helicopter. This is how you would look at it. But being this is a helicopter, that's the big difference. So let's say in forward flight, it is maximum, say forward flight is longitudinal when the blade azimuth is at 270 degrees, and is minimum when the blade is at 90 degrees. So the dynamic pressure is higher than this because just because of the forward motion of the aircraft. So, but QAD we found is also a function of the blade angle and the azimuth. So this winds up being 0 as you go around. Like if for each individual blade at any given point, it's going to be this here, but if you sum all 4 blades up, it always sums to 0. So, but anyway, if we look at it, our total Q is our Q average. It would be this plus this additional Q, which this winds up being 0. So, so anyway, the lift for each blade will then be when forward flight is added. So we want to change this to TOTX. So, but anyway, QTO2X winds up just being equal to Q average, because this Q add X winds up it winds up being 0. Now, when we look at the drag, say on the fuselage, then this comes into play, and then this is what we're trying to cancel with, say, the longitudinal X force in our rotor. So we're gonna look at this a little bit on our spreadsheet. So we say, note that the impact of Q add X cancels out between the blades. So we're going to look at this forward flight tab on the spreadsheet. Therefore, Q add cancels for both the main and tail rotors for forward flight. So forward speed doesn't impact lift and drag for the rotating rotors. However, one thing we want to make sure is Q add should never be greater than Q average. So if this starts becoming greater than the average Q, then you kind of get a negative. This Q total becomes negative, and that's something you don't want. It will cause the blades to stall, so that's something to avoid. So Q add should never be greater than Q av, otherwise there would be some negative dynamic pressure on the rotor. For lateral flight, Q add also cancels out for the main rotor, but not for the tail rotor. So here's some notes. So lateral cyclic for left-right motion will behave the same as longitudinal cyclic for forward-aft motion. So in the conventional helicopter, you could look as lateral cyclic is very similar to longitudinal cyclic in the way it works. And only in our case, only the fuselage drag will limit the X and Y forces. So the X and Y forces generated by lateral or longitudinal cyclic, we want to make sure that these X and Y forces generated will be greater than the fuselage drag. Otherwise, we won't have enough force to be able to move the aircraft. So that's the end of my notes here. So we want to look at our spreadsheets now to look at how this analysis might work. So the first spreadsheet we're going to look at is, I called it cyclic studies. So the way I set up these spreadsheets, over here on this side, I put parameters that are more fixed. So in this spreadsheet, we're going to look at a 0 to 360 degree rotation of the main rotor and see how things vary with azimuth of the rotor. So what I have here with these fixed parameters, the things in bold is an input. So these are parameters that we can vary. And the plain font are things that are computed. So the only thing you want to change are things that are in bolds here. So for example, we have we choose our RPM to be 250 revs per minute for this rotor system. And we chose the radius to be 20 feet of the blade and the chord to be 2 feet and the weight of the aircraft to be 10,000 pounds. Now this is our air density at sea level. So the vary altitude, if we need to vary altitude for this, we look at the standard atmosphere table and we could put a different row in here. So we could do parametric variations as a function of altitude. Right now this is just at sea level. So I have a lot of parameters in here. I'll try to go through these. So this is parameters mostly for the main rotor. So this parameter here is the rotor speed again in radians per second. So it's just a conversion, a straightforward conversion from RPM. And then we have our standard coefficient of lift, which is 2 pi. And this is our coefficient of drag for an airfoil that I got just out of a handbook. And this is a coefficient of drag for a flat plate going into the air. So these are pretty much fixed. We don't things that are plain or either computed or fixed that we don't normally vary, but you could possibly vary these if you found a better number for drag coefficients. So this is our surface area for the rotor, which is just the radius times the chord. So this is our average dynamic pressure for the blade. So we went through that equation previously. And this is this over here represents the lift of the rotor as a function of its pitch. So we had an equation for that also that we showed. It's basically just the coefficient of lift times this average dynamic pressure times the surface area, the 40 square feet of the blade. So this is like for one blade. So this would be what I call the D1 drag for one blade. It winds up coming out to 195 pounds. So by doing slight changes to this, if I change this to 255, say, you'll see everything in here change and update, which is nice. It's alive. It's like a live spreadsheet. So we can look at it at 255 RPM. I'll go back to 250 because that was kind of my baseline. So this is, so you could see, so right here the drag is 195 pounds of D1 drag. If I change this to 255, it goes to 203 pounds. It gets a little higher. The drag gets higher as a function of the rotor speed. So this is the kind of the fixed drag from the airfoil of the rotor, and this is the drag that's a function of the feathering or pitch, or the pitch of the rotor blade. So that's our D2 drag. So at this point, this is L4R is the lift of all four rotors. So basically, it's just the number of blades times the lift of an individual rotor. So this is a function of angle again, of pitch angle of the blade. So we want to compute, how much collective pitch do we need for the aircraft to hold its own weight. So the weight of the aircraft and everything in it, and everything it might be lifting is 10,000 pounds. So all we do is we take the 10,000 pounds and we divide it by this. And that gives us 0.0916 radians. So that says we have to have 5.24 degrees. This is it in radians, this is it in degrees of collective pitch on all the blades to be able to lift 10,000 pounds. So that's a good way to figure that out. So the collective pitch is basically a function of weight in this analysis. And then from that, we can figure out our drag of the four rotors. So the drag of the four rotors would be 4 times the D1 drag plus 4 times the D2 drag times this angle here. So that'll give us the drag of all four rotors in pounds. And that's working on that 3/4 of the distance, that 3R over 4 position. So from that, we can figure out the torque. So the torque winds up being 3/4 times the 20-foot rotor times this drag. So it winds up being 42,287 foot-pounds. And from that, we could take the torque and multiply it by the speed. That's this term here to get the power required to be able to turn that rotor. So this is good. So now I could figure out size of the engine for what size engine I'll need, or what size engine is available. So I need a 2012 horsepower engine to drive this rotor. So this is how you get into the analysis. It's kind of like a trade study, and you try to study it to figure out how you can optimize the design of this helicopter. So now I want to look at the cyclic inputs. So I want to move the aircraft forward. So a minus cyclic longitudinal cyclic input will make the aircraft move forward. It'll pitch the nose down. And likewise, a positive roll input will make the aircraft roll to the right. But anyway, I could put zeros in here, and you'll see a lot of these waveforms here. They'll change. A lot of these things with zero longitudinal cyclic and lateral cyclic, the blade pitch is this constant. It says 5.28 just to represent the collective. So I have some plots here. So I have the blade pitch and the blade lift. This is the lift for a single blade, and this is the lift for all the blades. And then I have the Z-force. So I'm going to include all these spreadsheets at my website that you could download and take a look at these to see how they're laid out. So this is the Z-force over here. So this is the total Z-force, which is the 10,000 pounds needed to lift against the weight. And this is per blade, which wound up being 2,500 pounds per blade. So the other things I have here are the X-force, the Y-force. So these are all cancel out to zero, like the total 0 is over here, and the total 0 for the Y-force. So if I put in the -1 again, let's look at the Y-force here. I'll put -1 in here. So you can see, yeah, now it goes to some constant. So it's 174 pounds. So if I put in 1 degree of longitudinal cyclic input, that generates 174 pounds of forward motion. So in a hover, like the drag would be 0, but in forward flight, I might not be able to overcome the drag in forward flight. So that's the thing you want to check to see if it's a feasible design or not. So likewise, if I put this back to 0, and I put in a lateral cyclic pitch, now the Y-force change. It's actually the same. It winds up being 174 pounds again. So it acts in the same way. Longitudinal cyclic pitch and lateral cyclic pitch act in the same way. So the neat thing about this, you get to see the waveforms like the X-force from each blade. So blade 1 is the blue line, and you can see how the force varies. This is what causes a lot of vibration in the aircraft too. So you could start looking at that also. So this would be blade 1, and blade the Y-force contribution from blade 2, which starts out as 0, and from blade 3 is over here, and blade 4 is the purple one. So it also looks at the moments. So this is the pitching moment. So the pitching moment, when I put a negative longitudinal cyclic command in, I get a negative pitch movement here. You can see it over here is the blue line that will make the nose of the aircraft go down. And then likewise, you can see I get a right roll moment in the airframe, which will tend to make the aircraft move towards the right. So it's interesting to look at these and see how these work. So what I also have in here is the tail rotor design now. So these are the inputs. I have a prop radius of 4 feet. So the diameter of the tail rotor would be 8 feet. So I only have a 2-bladed tail rotor here with a 1-foot chord. So likewise, the things in bold are inputs, and the tail rotor speed is really fast, 2,000 RPM. So I have a surface area of 8 square feet, which is the 4 foot times 1, but there's 2 blades. So yeah, I think I have the number of blades times the radius times the chord. So over here we have the tail rotor speed in radians per second, and likewise we have a Q average for the tail rotor, which actually is much higher than the main rotor because it's spinning so much faster and it's small. So then we get this lift of the thrust generated by the tail rotor as a function of its pitch. So we have the crank arm, and we picked 40 feet for that. So that's in bold, being it's an input. So So the tail rotor torque winds up being, this is like a torque as a function of the angle, and we'll compute what angle we need for that, the angle of the blade angle. So the torque winds up being this lift times this crank arm. So that's this 40 times 41 would be the torque. So we need to know how do we figure out the pitch, the pitch of the tail rotor. So the way we do it is we know from up here, we know what the it's B21. This is the torque from the main rotor. So this is the torque caused by the drag of the main rotor. So we computed that previously. It was a 3/4 times B5 times B20. So that's the drag times it's 3/4 of the radius of the blade times the total drag in pounds. So the way we get this pitch is we take this torque and divide it by this torque gain, and that will give us our tail rotor angle that we need, how much pitch we need in the tail rotor. So this is to stabilize, to cancel out that torque from the drag. So this is our anti-torque design here. So it winds up being 4.33 degrees. Now we also have drag of the tail rotor, so there's the D1 drag and the D2 drag, which is fairly a big number. So the total tail rotor drag winds up being 315 pounds in this case, and there's a torque of the tail rotor. It's the same way as the main rotor. You work it out the same way. And so this is the power required. So our tail rotor is taking an additional 360 horsepower. So if we add up the total power, we sum the tail rotor power and the main rotor power. We need 2,373 horsepower. So it's a pretty big engine. Well, it's a heavy helicopter, so that might be typical for a 10,000-pound helicopter that you need that much horsepower. So I also have a thing in here for tail rotor control. So if I go delta is beyond the 4.33. So this is to generate a delta torque. So if I need to have directional control to turn the aircraft to see if that's feasible. So if I put an extra degree in here, this generates negative. That allows me to turn I believe that's clockwise. Well, it added more pitch, so it causes counterclockwise. So it turns the body counterclockwise. So I needed, on top of the 4.33, it added 1 degree. So I didn't go back in and figure out the additional drag I would get, because that would take more power. So the thing for the tail rotor, you have to have some margin. Maybe I could feed that back in, and if I knew what the worst case tail rotor input would be, I could figure out the power. So if I put a -1, that's actually going to be less power. So that might be something to add to the spreadsheet, that I can add more details to that. So this would reduce the pitch of the tail rotor, which would allow me to turn to the right now. So put that in there. So this is the tail rotor. So now I wanted to do some checks here. So I wanted to look at a few things here. So one check is to make sure that the blade tip speed is less than the speed of sound. Otherwise, you get shock waves, and you don't want your helicopter blades running faster than the speed of sound. So the speed of sound at sea levels, 1,116.5 feet per second. So I computed my main rotor tip speed as being 525 feet per second, which is much less than the speed of sound. So I could probably make that rotor actually spin faster without any issues. Now for the tail rotor tip speed is actually running a lot faster. It's running 837. So that's getting closer to the speed of sound you probably want. But maybe that's a pretty good design. But anyway, yes, the main rotor blade tip speed is less than the speed of sound. The tail rotor tip speed is less than the speed of sound. So that's one check you can do. So there's a maximum forward flight. So I want to look at when what max speed is where Q add is equal to Q average. So that tells me that if I go beyond the speed, I'm going to have negative dynamic pressure, which will stall out the blade. So I put this in. This should actually be bold. This is my input here. So I'm going to make this bold. And so when I put 179, our average, our Q average was computed at 108.61 back here. That was it there. So I just bring this down here. So I know at 179 knots, I'm approaching 108.47 pounds per square feet. So I know that this helicopter probably isn't going to be able to do over 179 knots without stalling out the rotor. So that's my maximum forward flight maximum. Here, I'll make that red. And some other things. So this helicopter, you should never go over 179 knots. So with this helicopter. Okay, so the next thing to check is the centrifugal acceleration. What's the G-force at our blade tips? Because we want to make sure the materials can withstand that. So for our main rotor, it's the G-forces are very high from the centrifugal force. So for our main rotor, it winds up being 426 Gs, which is a typical G-force for a main rotor. So you have to make sure your structures can handle that, such a high G-force. The tail rotor centrifugal acceleration is even much higher. So this tail rotor might not be such a good design. I mean, having 5,453 Gs, that tail rotor is really spinning. Maybe a slower tail rotor, slower but bigger tail rotor might be better for this design. So anyway, this is the trade studies you do to try to investigate this. All right, so if we look at the overall spreadsheet again, I'm going to bring this up. And yeah, so I plot out the forces. And so this is a good tool for doing your initial investigation at hover. So this is the tab I have for hover. Now for forward flight, I also did an analysis where I used that the total Q, and what I saw was the drag. The overall drag all cancels out on the main rotor. So like here I had 218.95. It's a constant, although for all the blades it varies all over. But so this was an example, say at 100 knots. I added I believe yeah, see, this is my forward flight over here. So I added some columns here to add in this Q add that I showed on the equations. So, but anyway, you could see the drag here, the constant drag here, 218.9.15 was the same. So it shows that that it all cancels out. This additional dynamic pressure from the motion of the helicopter cancels out. So now we'll go to the second spreadsheet where we could do the parametric variation. So this is where I started to add in the drag from the fuselage, and I'll put this on my website so you can have access and see how this is done. So it's similar to the first spreadsheet that you saw, except I make a baseline column, and the trick is in your computed value is to just put the dollar sign after the letter. So we want to vary the we want to vary the letters, but we don't want to vary the numbers when we cut and paste to do our parametric evaluation. So we could do a good parametric evaluation is to vary altitude or vary airspeed. So we're going to look at a variation in airspeed. So this is all the same stuff again, but I don't have any plots here. And so I brought out it's like a static point, and so these are all of our forces again computed out. And you can look at that in detail if you're interested in doing something like this. So, but the the big thing that was added was just the drag from the fuselage. So I assume that the width of the fuselage is 10 feet and the height is 10 feet. So there's going to be some drag, X-force drag from the fuselage. So at 0 knots, it's basically zero. There's zero drag, but I could generate 174 pounds. But let's say I did change the airspeed to 100, so I'll put 100 in here. So say the forward flight of the aircraft's 100, so everything will update here that needs to update. So now you can see, yeah, the drag at 100 knots is 1,015 feet. So I can't and at that, and my drag force is actually the other way. With I have 1 degree of longitudinal cyclic pitch in here. So I could change this to change the X force. So I can I'm actually short. I'm actually going backwards here. So I'm generating a backwards force. I'm not able to overcome the drag. So I want this X force to be greater than 10,015. So if I put maybe I've been through this before. Well, I'm going to put 0 in here for lateral. Not worried about lateral here right now. So I think if I put -6 in here. Yeah, so when I put -6 in there, I'm generating a little bit of positive X force. So about 25 pounds, so I can just about move forward. So this tells me the design is feasible. That's if I can do 6 degrees of longitudinal cyclic pitch. It might be limited by the mechanics. But anyway, I did a whole parametric variation here from 0 to 150 knots. And I tried different longitudinal cyclic pitches. So I plotted out airspeed versus the cyclic pitch. So I start at 0, -1, -2, -3, -4, -5, -6, -7, -8, -9. So the green means I could generate a force, a longitudinal force to overcome the drag of the aircraft, and the red means I can't when it goes negative. So say at 5 degrees, if I could do 5 degrees of longitudinal cyclic pitch, I could go up to where it's green here. I could go up to 100 knots. So I can make this helicopter fly up to 100 knots. Now, if I can achieve more cyclic pitch, say the 9 degrees -9, I could go up to 120 knots. So this tells me, yeah, I might have requirements for this helicopter, and I want to make sure that I meet the requirements. So if I can't do this and I can't meet the requirements, I might have to change some things to get a better design. So this is the typical parametric variation. So now this is at sea level, so you want to do this at all the other altitudes by changing the air density, So anyway, this is a sample on how to do this kind of work, and if you have to design a helicopter, a conventional helicopter, this is how you might go about it. And just wanted to go through this to show you an example, and keep on working this. Hi, so I didn't want to bore you, but this is what you have to go through to analyze a conventional helicopter. So I hope you enjoyed this and hope you got something out of it and learned something. I couldn't find many books on doing this. I'm pretty sure there's probably something out there, and I'm pretty sure there's a lot of other ways of doing it and a lot more you can learn. So read the books on aerospace and helicopters and see what you could add to this, and it'd be interesting to add more details to this to get an understanding of helicopters. And this helped me a lot with the model helicopters I like to work on to try to get a better understanding of them. So bye now.